Hello and welcome to our very first lesson of the MCV4U Calculus course. My name is Miss Ganji and I'm going to be your instructor throughout this course and I'm very excited to follow your journey as you learn calculus. So for our lesson today, our learning goal is to go over some prerequisite skills you need to get you started for the calculus course, as well as to figure out what calculus is. With algebra and functions, you've heard of them, especially algebra, you hear it throughout middle school, and functions you hear throughout high school. But then comes calculus in grade 12, and some of you may be wondering, what is calculus? So, calculus started as two geometric problems with consideration to the graph of y equals f of x. So the first problem that they were wondering was the problem of the tangents. So for any point P, on our function of y equals fx, we want to know what's the slope of the tangent at that point. And if you recall, a tangent is a straight line that crosses um, a parabola or intersects a graph at specifically one point. So we want to know what the slope of that line intersecting the function at any point P would be. And our second problem is the problem of areas, where we wonder that for any two given points, A and B, if we limit the domain of our function, what is the area under that graph specifically? So for example, here, for A and B, we want to know what that area is. And so, throughout history, many mathematicians, including Archimedes of Syracuse and Sir Isaac Newton, tried to work on these problems. And it wasn't until René Descartes and Newton and um, Leibniz figured out how to solve both of these problems. And so Leibniz, you'll see his name a lot throughout math, and he specifically has a notation when it comes to calculus, which we'll see shortly. And so they figured out how to solve these problems using two different ideas, differentiation and integration. And we're going to start our calculus course specifically with differentiation and derivatives, and that's going to be a big part of our calculus course. And so calculus as a whole is the mathematical study of continuous change using differentiation and integration. So let's refresh a little with some background information we need to know, starting with rational numbers. So a rational number is any number that can be expressed as a fraction containing integers. And you've seen rational expressions as well, so any expression that can also be represented as a fraction. So our idea, which is a big prerequisite skill that we need, is to rationalize numerators and denominators. And what that means is to change a radical or square root, either from the denominator or the numerator, into a rational number of an integer. So, for example, in this example we have here, we're changing the denominator from a square root of 5. And how we do that is we keep our first fraction and we multiply by the square root of 5. And why we do this is now in our denominator, the square root of 5 times itself is just 5. And now we have moved the square root into the numerator, so we've rationalized the denominator. And this is an important skill that we're going to be practicing. Now, sometimes our fractions are not just going to be a simple square root or a simple radical. And sometimes you'll have an expression where it has two terms. It'll be a binomial, such as square root of A plus square root of B. And in this case, we have a conjugate, which is just the same two terms, but then instead of adding, you're now subtracting. And same would apply if we have square root of A minus square root of B. This has a conjugate of square root of A plus square root of B. So this works vice versa. So let's try this now. I'll give you a moment to try this on your own to multiply these two square roots. So if you try to expand using FOIL, so we um, first multiply the first terms, the outer terms, the inside terms, and the last terms. So you'll see that you get A plus or minus square root of A, or sorry, square root of AB, um, minus, well, this one should be minus square root of A, B, And finally, and the middle two terms here are going to simplify out. And so all we're left with is that A minus B. And so we've actually been able to find a more simpler expression that doesn't use those radicals in there. And now let's try simplifying this by rationalizing the denominator. So starting with the conjugate, because we have two square roots added, the conjugate will be the same square roots, but now subtracted. So we start with our fraction. And remember, we have to multiply both the numerator and the denominator by that conjugate. And the reason for that is if you are multiplying the numerator and the denominator, this fraction is actually equal to just 1. So you're not changing your equation, you're just multiplying by 1 or an equivalent of 1. And now in the denominator, we're going to see that we get 6 minus 3, and in the numerator, we will just leave it as such. And now this can be simplified to the following rational number. So we have the two fractions and we don't have a radical in our denominator, which is what we wanted by rationalizing the denominator. So here, I've given you now another example, and I want you to consider why this is different from this example we saw here. You should have noticed that here we have two square roots in our denominator, whereas here we only have the square root in the first term. And how does that make a difference for our conjugate? So as you can see here, this is my conjugate term here. And you see that I am still keeping the same two terms. So uh, if we let A be 2 square root of 6, we see that A term. And if my B is 3, then I kept that 3 there as well. The only difference is the sign in between the two terms, which changes from a positive to a negative in both of these. And if you recall, this is still that 1. And now, if we multiply through, in the numerator, we just have that 5 times the bracket. You can just keep it as such for now. And in the denominator, we have the square of the first term, so A, square of A. And in the second term, we have the square of B. And this can actually be simplified. I just wrote it this way for you to see that this is the equivalent of here, but this could also just be 2 times 6, or sorry, this should have been 36. 2 times 6, which is, oh no, hold on. Let me rewrite that. This is 2 square root of 6, which is 4. And what I did was take the square and apply it inside the bracket or inside the square root to give me this, but this is the same as 4 times 6, which is 24, and that's what you see over here. So if you had skipped a step here, that's fine too. I just wanted to show you, especially since we're just starting to learn this, so you see exactly what step takes place. Now we just simplify our denominator to that 15, and I can see that I have a 5 and 15. So all I will do is just simplify that. So now uh, I have rationalized the denominator, and I don't have any radicals in my denominator, which was my original goal. So for this question, I want you to consider, why do we have to include that 2 in there as well? Why can't we just multiply by square root of 6 minus 3 as the conjugate? Because I'm still considering the square root and I still kept 3, but why is that 2 relevant there as well? So to see that, I've shown you here that if you try multiplying by this value or this conjugate without that 2, in the denominator, you actually get this as our expansion. So if you expand by FOIL, you will get these 4 terms. And The middle two terms actually in this case do not cancel out because you have -6 and +3, which is, I hope you see the difference of that 2 there, which would have given you a 6 here. And so we do not actually simplify our denominator. We're just still left with two radicals, which you can simplify them into one, but we still will end up with a radical. So this will not work to rationalize our denominator. So you need to keep the same a and b value and just change the operation from addition to subtraction or from subtraction to addition. So try this on your own now and simplify this expression. This is actually one of the simpler ones of the first example we saw. So I just wanted to show you for this one as well. It's pretty simple. All you would be doing is times that square root of 5. And in this case, because it is only, it's not a binomial, it's just a monomial, you don't actually have to multiply by that 3 because this on its own will give us that 5 in the denominator. So we are getting rid of our square root. And in the denominator, you can combine the two square roots to get square root of 30. And here we can just leave it as such. And this is our simplified expression. So to give you a definition for this practice problem, if you have a radical expression of the form square root of a over square root of b, this one can be simplified by just multiplying by the square root of b that's in the denominator. And this is regardless of any coefficients. And the reason for that is, consider this example above. I can just factor this into this expression. And now my only term with that needs to be rationalized in the denominator is this one, which is that a and b, for a being 6 and b is 5. So then this is essentially what I did. I multiplied by square root of 5 over square root of 5 to get, and we saw here 30 is our ab. And the coefficient can come back later, but you don't need to consider it when you're trying to rationalize your fraction. Now, another prerequisite skill we need for calculus is to calculate rates of change, starting with our linear rates of change, which comes from slope of a line. So the slope of a line is just the rate of change of the line, which remember is just the rise over run or how much the y value is changing with respect to the x value. So consider 2 points A and B, where A is has coordinates x1 and y1, and B has coordinates x2 and y2. Then the slope of the line connecting these 2 points is defined with, we use the variable m, and it's the change, this one should be y over x. So we are considering the change in the rise over the run, which the rise we get from our y values, how much we're going up or down, and the run is how much we are changing horizontally, so how much our x values are changing. And we can also write the equation of a line, specifically when we know the slope m. We will use the y equals mx plus b expression, and we calculate b, where b is the y-intercept. And again, if you have m, this can be easily substituted there for any point A or B. You will substitute y and x, and you can calculate for b. One note here I'll add as well, which you might see throughout the lesson, is the standard equation of a line, which this one is just when you move all the terms over and write this as an equation equaling to 0. Recall it's the same with standard form of a quadratic where we have ax squared plus bx plus c as equal to 0. These two are both the standard form. We just have one as the standard form of a line, and the top one is the quadratic standard form. Now, we're now going to start making connections between those and some things we see in calculus, starting with a secant. So a secant is just a straight line that intersects a curve at 2 or more points. So consider a quadratic such as this, and let's say we have point these 2 points. So the line that goes through these points and it intersects the curve at these 2 points is called the secant. And we can apply the slope of a line to find the slope of the secant. We also might have what's called a tangent. So on our quadratic, let's just use that example as well, I can have one specific point, and the tangent will be a line that intersects this curve at exactly that one point without crossing it. And the tangent represents the line that goes through here, and we can also find the slope of the tangent at that point. Now, we are going to be looking at average rate of change and instantaneous rate of change in connection with secant and tangent, starting with average rate of change, which we see in this lesson, and we'll see instantaneous rate of change in our next lesson. So an average rate of change is pretty much how much your speed or your position is changing with respect to the time, which gives you the speed. So if we have our position given by s of t, the function s of t, at a time t, then the change of the position with respect to time can be given by change of s over change of time. Now, consider that an object changes positions from t is equal to a and to t is equal to a plus h. So our starting time is time a, and after h amount of time, we can determine that the change in the position or change in s is given by the new position, so s of a plus h, with the difference of the starting position, which was S of A. So again, remember, this is the starting position, and this is our ending position. And that's if we're considering the change from one point to another point, or from one time to another time. And we can write that the average velocity over this time interval is given as the change in the position over change in time, or the change of s over change of t. And this can be represented now with the values of the function, so s of a plus h minus s of a. And in the denominator, our change of t is also that end time, which was t of a plus h, and our starting time, which was just a. So a plus h minus a, and this is just simplified to h. And this is the average rate of change for a moving object. So now let's look at it in an example. Hopefully that makes a little bit more sense when we apply it with a real world problem. So consider the function s of t is equal to 6t bracket t plus 1, which describes the distance in kilometers that a car travels after a time t in hours. And we're looking specifically at the time interval of the first 6 hours, because our t is between 0 and 6 inclusive. And we want to find first the average velocity between time 1 and time 3. So to do this, we are first going to find s of 1 and s of 3. So our starting position and our ending position. So substituting this into our expression, we get here 12, and here we get 18, and 3 plus 1, 4. 72. So over 2 hours, our position in kilometer changes from 12, and remember these are in kilometers, 12 kilometers to 72 kilometers. So think of this on a line, and this is just our position. We go from 12 to about 72, and this will take us 2 hours. Now, to find the average velocity, we want to find that change of s over change of t. So our change of s is going to be, and let me just write it with this first. And so I hope you can see that here the change of t is just 3 minus 1. And so in the numerator, we have 72 minus 12. over 2. And this will give us 2, which is 30. And now I want you to think, what is the unit here? Because in the example above, because we were talking about a general example, I didn't give you any units, but here we have units. So consider the numerator where we have change of s. This actually has a unit of kilometers because our distance is given in kilometers, and our time was given to us in hours. So here, we have our unit as kilometers per hour. So the average velocity between time 1 and time 3 was 30 kilometers per hour. So that means between the first and third hour, they were probably driving at a speed of 30 kilometers per hour because remember, speed and velocity are the same. Now we are also going to try the average velocity between time 1 and time 5. And it's a little bit easier for us because we already have s of 1 equal to 12 kilometers. So now we will just find s of 5, which I'm just going to rewrite this here. So substituting 5, we have 180 kilometers. And so here, the change of position with respect to the change of time is given to us as 180 minus 12. And this time, for time, we actually have 5 minus 1, or 4. And so in the denominator, we will have, or in the numerator, we will have 168 over 4, and this will give us 42 kilometers per hour. So that same unit with the same justification as above. And so you're asked why the average velocity in part A and B are different. So consider that the position was given to us by the function s of t, which is actually a quadratic function. So that means the rate of change of the position is not consistent over time. And think of a real example as well. The car may be speeding up at times or slowing out at times. And so if we consider between T1 and T5 that it has a average velocity of 42 kilometers per hour, we can probably conclude that in the last 2 hours, from T3 to T5, they probably sped up a bit, and that's why their average velocity increased. They probably actually sped up way more than in the first 2 hours to achieve an overall higher average velocity. And I encourage you here, you can try on your own, but calculate the average velocity when t is between 3 and 5 to determine what the average velocity was there and compare that to the overall for the 4-hour block. And so that is the end of our lesson. So today's lesson was a bit shorter because I want you to clarify anything of the prerequisite skills that you might need and to familiarize yourself with the course. For this lesson as well, you have a gizmos task, which you can look at how arithmetic and geometric sequences are changing and if they approach a certain value. So I highly recommend you to try that. And if you have any questions, please don't hesitate to reach out. And that's it. You're done lesson 1 or first video lesson. And I will see you all in future lessons.